Right, hello again. We're going to continue on with 10.5. Like I said before, I've divided this up into two parts. 10.5a, which you've just seen. I'm doing 10.5b now. It's all the same part of the textbook. Starts on 289 and just continues on. This is the New Century Physics book for Queensland, in case anyone else besides you happens to watch this. This is this great text you're using. Now look, the reason I had a break is I wanted to get the two graphs drawn up. Now these aren't in the text, these are different, and that just gives you an extra example if you want to work with them. So I've got two to look at, a complicated one. Now I'm just going to cover up a part of this complicated one so it doesn't distract you. So I'll just put a bit of paper there, and I want to look at this one here. Now what we've got, now this is in meters per second of course, and this is t in seconds. So what we've got is an object that appears to be doing this. For the first 10 seconds of its journey, it starts at rest, that's zero speed, is called at rest, and gets faster and faster until after 10 seconds it's doing 100 meters per second. Now that's really flying, that's much faster than a car would do, that's hundreds of kilometers an hour. You know, it could be, well, it could be anything. Let's imagine it's something that can go really fast. Maybe a bullet. No, it wouldn't be a bullet. Let's imagine it's a very fast train. Okay, so after 10 seconds, what it's doing is it's keeping a constant speed of 100, or constant velocity of 100. Then after that 10 seconds is up, so in other words 20 seconds has gone past, it's going to start to decrease its velocity, and it goes back for the next 5 seconds. It's slowing down until it's back at rest. So speeding up, constant speed, slowing down. Okay, that's all that means. Now a typical question for this, it would be calculate the distance travelled and calculate, say, the acceleration for the different parts of the journey. Okay, let's have a look at the distance. Now the distance travelled is just the area under a VT graph. So I'm going to break this up into parts A, B and C, just to label it to make it easier. Now the area is going to be the area of A, which is base by height on 2. So it's 10 times 100 on 2. So 10 times 100 on 2, and that comes to 500 metres. Okay, now the second part of the journey is B. So this is part A. B would be base by height. Now it's a rectangle, so it's base by height. So that's 10 times 100, which is 1,000. So it took 500 metres to get up to its maximum speed. And then for the next 1,000 metres, another kilometre in other words, it travelled at constant speed. And then for part C of the journey, base by height on 2 for the area, so it's 5 times 100 on 2, and that's 250 metres. So it came back to rest much quicker than it accelerated at the beginning. Now this is just a made up one. So the total is just the sum of all this, which is 750 metres. So that's your answer to that. That's how long it took to do that. Now you could also be asked to work out the acceleration at the different stages. Well, the acceleration is the change in velocity divided by the time. In other words, the gradient. So the gradient of that is 100 on 10. So that's 10 meters per second squared. So that's the acceleration. 100, that's the change in velocity divided by the time. It's 10 meters per second squared. This thing here, for the next 10 meters, there's no change in velocity. So A equals 0. And here, change in velocity is 100 divided by 5, and so that's A equals 20 meters per second squared. So it's slowing down faster than it's sped up. Now if you had to draw an AT graph of that, look, I didn't think to do this, but if you had to, you'd put TA, so it was 10 to start with, and then it dropped to 0, went to 0 for a while, and then for the last 5 seconds it was at 20. So it's up here like this. So 0 to 10, 10 to 20, 25. So that'd be the shape of the graph. Now, if your train did that, you'd probably break your neck, because you're going from an acceleration to nothing in, basically, according to this, it's in 0 time. I've made that a sharp change from 10 to 0. In real life, this would be more, you know, in real life on a train, it'd be more like a curve. Okay. Now, if it was like that up here, well, you'd never, you'd break your neck, as I said. So what it would really look like, that'd be a bit of an angle there. So the acceleration didn't go from 10 to nothing in 0 time. It took a fraction of a second to do that. Now that's what all that stuff about change in acceleration, which was the jerk, would look at. So you could work out the jerk, the amount of jerk for that. Now I think they allow something like 50 units of jerk as the maximum, which would be a change of acceleration by 50 units per second. But we're not going to do that. And the same here. It'd go up like this. Okay? But the acceleration graph would look something like that. Now you'll get questions where it's done like that. But you have to think, if you're an engineer at uni, and you finished uni and you're an engineer, I mean, you'd look at that and you'd say that doesn't even make sense, those sharp lines. But just for the purposes of the senior physics part, that's what we've done. Some of the questions they use is something like a bungee jumper, and it's the displacement of a bungee jumper, or someone on a skateboard or something like that. But what they're doing, velocity versus time again, but you'll notice I'm going down into the negatives, so that's a bit tricky. You know, it's going to make some complications for our work. So this will be minus 10 and minus 20, okay, because it's negative velocity. Now you know, I've told you before, that's the positive direction, and this would be the negative direction, just like a number line. So in a lot of ways, what the object is doing is going for a velocity, a positive velocity, to start with, and then slowing down, getting back to 0, and then going in the negative direction. Okay, so it's going like that, and that could be a bungee jumper, or it could be something on a spring oscillating back and forth. So the first thing to do is to work out the distance travelled. That'll be the first question. Distance travelled is just the area under the curve. So let's call this A and this B. Okay, you've got two triangles. So the area of A is just base by height on 2. So it's 20 times 10 on 2, and that's 100 metres. Okay, now that's positive because it's plus 10. Base was 20, and the time is always positive, times plus 10 over 2 comes to a plus 100. The area of B is just base, which is from 20 to 60, so that's 40, times the height, which is negative 20 on 2. So that's, it's getting a bit squashed here, negative 400 metres. Now if you work out the total of that, it's just comes to negative 300 metres. So the question is, what does that mean? All it means is that it started here at 0, went 100 metres in this direction. Okay, so there's the 100 metres until it came to rest. So let's say it's a person running. They ran for 100 metres. They sped up for the first part until they reached a maximum velocity. So they're running fast, they reach a maximum velocity, and they get a bit puffed and they slow down. And by the time they get to the 100 metre mark, they're travelling, they're back to 0, so they've come to rest. So it's a person running 100 metres. The first part of the journey, they go fast as they can, and they reach the maximum speed halfway down the track, and then for the second half of the track they slow down because they're puffed and they end up at rest. But once they're at rest, they don't stay at rest for long. They start running again, but in the opposite direction. So they've run up, they've slowed down, stopped at the 100-metre mark, and now they're running backwards for whatever reason. So they're running backwards for a total of 300 metres. So they got to that point, and then they ran back. Whoa, I'll make it so you can see it. There's 100, 100. So they ran back 300 metres, so they're to this point here. Okay, so it's in the negative direction, and that's about all. So the total, no, they ran 400, sorry. That's better. So that's 300 metres in the negative. So that's why it's the final displacement is at this point here, which was 300 metres in the negative direction from the zero, and that's all that means. Okay, so if you can see that, that's all there is to this stuff. Now if I said to you what's the distance travelled, well, they've done 100 and 400. Remember, distance is not a vector quantity, so this negative business here only applies to vectors and therefore velocity. So this is the displacement, and the distance is just 100, which I had in here, plus 300 comes to 400. So the distance travelled is 400 metres, and that's all there is to it. So you ignore the negative part when you're doing distance. Now I'm just going to finish this off by looking at the acceleration at the different stages. So I'm going to rub this off and get rid of all of that. We don't need this, and we're just about done. So you could look at the acceleration at the different stages. Now the acceleration from 0 to 10, if you like, this is time. Acceleration is change in y divided by change in x, or change in velocity divided by time. So that's 10 on 10, so that's plus 1. So A is plus 1. This part of the journey, it's gone from 10 to nothing, so that's a change of negative 10. Remember, it's final minus initial, so final is 0, initial was 10, so it's negative 10 over 10, so that's negative 1. So from 10 to 20, it's that. From 20 to 40 seconds, well, the gradient's still the same, so this must be negative 1, but let's have a look. It's final, which is that, so it's negative 20 minus initial, so negative 20 is the final here. Initial was 0 over time. Okay, so negative 20 over 10 is negative, what? Negative, oh that's over, oh sorry, over 20 seconds. Okay, because I did it, 20 to 40 is 20 seconds. Wait a minute, what happened here? Yeah, that's right, 20 to 40, this section here, change of negative 20 divided by the 20 seconds comes to negative 1. And then back here, now this is the tricky bit, this is where everyone gets tangled up. The acceleration here is, look, I'm going to do this one, it's final minus initial, so final, which is 0, what am I doing? Final velocity is 0 there, minus the initial velocity, which was 20. So that's minus 20, okay, over the time. So that part took 20 seconds. Now you know, minus and minus, you subtract a negative, it's like adding a positive, that comes to 20, so it's plus 20 on 20 equals plus 1. And so this is 40 to 60, it's plus 1. Now you might think, what's going on here? We're down in the negative side of things, and how can it be plus 1? The answer is, what's happening is, if you remember, the person was, there's the 0 point, they got to here, and then they were running back this way until they were at the 400 metre mark, well, they'd gone 400 metres, but they were at the 300 metre mark, I think. No, they're 400 metres. That's right, I think it was something like that. What was it? No, they'd gone 400 metres, so they were back to negative 300 there. That's a 0, that's plus 100. That's better. So they'd come a distance of 400, but they're at the 300 metre mark in the negative direction. Now all that's happening is this person is running, they've stopped, now they're running in the negative direction. They reach a maximum speed. So what they're doing is they're there and they're reaching a maximum speed somewhere in here, and then they're starting to slow down, and they're slowing down until they get to here and they're back at rest. Now the thing is, when they're slowing down, it's like they're being pulled this way. There's some sort of force. Instead of continuing at the same speed, high speed, it looks like there's some force pushing them that way or slowing them down in that direction. Now we say because the force appears to be directed in the positive direction, the acceleration is in the positive direction. So even though the person is continuing to travel in the negative direction, the acceleration is in the positive direction because it's making them slow down. It's like they're being held up by some force that's coming from the positive direction, or they're being pushed in the positive direction at the same time. It'd be like running into a headwind, but you get to a maximum speed and then you get this big wind that stops you from running, and the wind is so powerful it brings you to a halt. Even though you can keep running, you get slower and slower in that direction, get slower and slower. So I should be doing it like this, getting slower and slower until you finally stop. Okay, and that's the interpretation of that. Okay, if you can see what's happened there, now you'll get questions where that angle is a bit different and so on. But that's the logic behind all of that. So we've done 10.5 A and B. You're able now to do the CYL questions on page 292, and that's it. So thank you for that. We'll see you on Monday, probably. See ya.